For decades, the moon seemed dead, silent, and fully understood nothing more than dust, rock, and empty darkness. But new discoveries suggest something far stranger is happening beneath its surface and inside its coldest shadows. Water, toxic dust, extreme cold, and hidden resources are transforming the moon from a lifeless world into one of the most important places in the solar system. Today, we explore the strange lunar mystery that could change humanity's future in space. Let's find out. The moon is 238,900 miles from where you're sitting right now. That's closer than Los Angeles is to New York. If you drove across the country 30 times, we've watched it rise and set for our entire lives. We know the moon, or so we thought, because right now, hidden on that ancient, familiar surface, there are places where sunlight has not touched the ground in more than 2 billion years. 2 billion years? Let that settle for a second. The first complex cells on Earth didn't exist yet. The continents were unrecognizable. The ancestors of every fish, bird, insect, and human being that has ever lived had not yet been born, and these places on the moon were already dark, already waiting, already frozen in a silence so absolute it defies imagination. These regions have a name: permanently shadowed regions, or PSRs. They sit at the lunar south and north poles, buried deep inside enormous impact craters, some of which stretch wider than the state of Delaware, with walls rising several miles into the airless sky. The moon's axial tilt is only 1.54 degrees, almost perfectly upright compared to Earth's 23.4-degree lean. That tiny difference changes everything, because the sun never rises high enough over the lunar poles to reach the floors of these craters. Not once, not in billions of years. The geometry of this world locks certain places in eternal night. To understand the darkness we're talking about, try this. Imagine you're standing at the bottom of the Grand Canyon, 1 mile below the rim, walls of ancient rock towering over you on every side. Now imagine the sun never crosses that patch of sky above you. Not today. Not in 1,000 years. Not ever. That canyon stays dark every single hour of every single day, through every season, across deep geological time. That would be extraordinary enough. Now multiply the depth, multiply the isolation, and stretch it across not thousands, but billions of years. That is what a permanently shadowed region is. And that comparison still doesn't fully capture it, because the Grand Canyon is full of air, full of life, full of chemical processes that slowly reshape stone and soil. The PSRs have none of that. Nothing happens there. Nothing moves. Nothing changes. They are, in the most literal sense possible, dead. The temperature inside these craters drops to negative 248 degrees Celsius, negative 414 degrees Fahrenheit. To put that in perspective, the surface of Pluto, the most distant dwarf planet in our solar system, averages around negative 225 degrees Celsius. These craters on our own moon are colder. They are among the coldest places in the entire solar system. Some scientists believe they rank among the coldest stable environments found anywhere in the known universe. And then, just a few kilometers away, everything flips. On the rims of those same craters, on the high ridges that catch the low-angle sunlight skimming across the lunar poles, the temperature climbs to positive 127 degrees Celsius, 260 degrees Fahrenheit, hot enough to boil water, hot enough to cook food. You could stand on the sunlit rim of Shackleton Crater, and just 2 miles beneath your feet, the ground would be colder than anything on Pluto. No atmosphere exists to smooth that out. No wind carries heat from one place to the other. The moon simply holds both extremes at once, separated by a few miles of vertical rock. This is the environment that the United States, China, India, Japan, and the European Space Agency are all pouring tens of billions of dollars trying to reach. Not the smooth equatorial plains where Apollo landed the safe, flat and sunlit regions. They want the poles. They want the craters. They want the coldest, darkest, most hostile terrain on the lunar surface. Why? Think about what you would have to believe to justify that. You'd have to believe that something exists in that deadly darkness, something valuable enough to send robots, and eventually human beings, into one of the most extreme environments in the known solar system. Something worth the engineering nightmares, the budget overruns, the years of planning and risk. So here's the question, and think about this. Honestly, what do you think could have been hiding in that darkness for 2 billion years? Scientists call these craters cold traps, which, honestly, sounds almost cozy, like something you'd see labeled on a nature trail map. Cold trap. Overlook 1 mile. Bring water. The name gives absolutely no indication that you're describing one of the most extreme environments in the solar system, a place where NASA's most advanced robots are not guaranteed to survive a single lunar night, and where human beings cannot currently walk without dying within minutes. Cold trap. Sure, that's like calling a Category 5 hurricane a brisk afternoon, but the name carries real meaning. A cold trap is any surface so frigid that molecules striking it cannot escape, they stick. They freeze instantly, permanently, before any force in that environment can dislodge them. And if molecules of a very specific substance have been drifting across the lunar surface for 2 billion years, bouncing and migrating under the influence of sunlight and gravity, and if those molecules eventually reach a cold trap, they stay there forever. So here is the thing that has sent space agencies into a quiet, multi-decade frenzy. Here is the reason that the most contested real estate in the solar system is not a tropical island or an oil-rich desert, but the frozen floor of a 2 billion-year-old crater on our closest neighbor in space. Whatever has been collecting in those cold traps, whatever got caught by temperatures colder than the outer solar system, has simply been sitting there, perfectly preserved, untouched by time. And if what's been collecting there is what the data increasingly suggests it is, then every space agency on Earth has been right to treat this as a matter of civilizational urgency. Because what's hiding in the darkness of the lunar poles isn't just scientifically fascinating, it's strategically invaluable. It could determine which nation leads the next century of human expansion into space. But in that deadliest place in the cold and the silence and the 2 billion-year dark, someone found something that had absolutely no right to be there. And once they found it, the entire future of human space exploration had to be rewritten from the ground up. But in that deadly darkness, something was found that had no logical reason to exist there. And once scientists understood what it was, the entire future of human space exploration had to be rewritten from the ground up. Start with the basics, because the basics are genuinely strange. The moon has no atmosphere, not a thin one, not a weak one, essentially none. The atmospheric pressure at the lunar surface is around 10 to the power of -12 bar. That is 100 billionth of Earth's sea level pressure. For practical purposes, the moon is a perfect vacuum, and in a perfect vacuum, liquid water cannot exist. The physics are absolute on this point. Without atmospheric pressure to hold it together, liquid water exposed to the surface of the moon would immediately begin to boil. Not because it's hot, but because there's nothing pressing down on it, nothing keeping its molecules from flying apart. It would vaporize instantly. Then, with no gravity strong enough to hold that vapor in place and no atmosphere to contain it, those water molecules would drift upward and eventually be lost to space. This is not a controversial claim. It is basic thermodynamics. And for most of the 20th century, it led to a near universal scientific consensus. The moon is dry, bone dry, dead dry, one of the most dehydrated objects in the solar system. Any water that ever made contact with the lunar surface would have been gone within minutes of arriving. So why is there water ice on the moon? The answer lives in the same craters we just talked about, the permanently shadowed regions. And the mechanism that makes it possible is, once you understand it, almost elegant in how quietly devastating it is. Picture a single water molecule. It arrives on the lunar surface carried there by a comet impact, or embedded in a meteorite, or assembled piece by piece from hydrogen ions in the solar wind, reacting with oxygen locked in lunar minerals. That molecule sits on the surface. The sun hits it. It absorbs energy, vibrates, and hops. It doesn't stay in one place, it skitters across the surface, bouncing from grain to grain of lunar regolith, migrating slowly across the landscape under the influence of sunlight and gravity. This process is called thermal hopping, and on the sunlit parts of the moon, it inevitably ends with the molecule gaining enough energy to escape into space entirely. But some molecules, purely by the geometry of their migration, drift toward the poles. And at the poles, some of them reach the rim of a crater and tumble down into a permanently shadowed region. The moment a water molecule enters a PSR, the game changes completely. The temperature is negative 248 degrees Celsius. At that temperature, the molecule doesn't have nearly enough energy to bounce again. It strikes the surface and it stops, permanently. The cold trap has caught it. And because the sun never reaches that floor, because nothing ever disturbs it, because no geological activity, no erosion, no weather exists to alter it, that molecule stays frozen exactly where it landed. For 1 million years, for 100 million years, for 2 billion years. Think of it this way. Drop a single ice cube into liquid nitrogen, and it freezes solid before it has time to melt even a fraction. Not a drip, not a drop. It goes from ice to colder, denser ice in less than a second, locked in place before any process of change can begin. The PSRs do something similar to water molecules, except instead of seconds. The timescale is geological. The trap is so cold and so permanent that molecules arriving across billions of years have been accumulating there like sediment, layer by microscopic layer, undisturbed. Where do the water molecules come from? Multiple sources. And this is where the story gets richer. Comets are the most dramatic delivery mechanism. Ancient dirty snowballs from the outer solar system that occasionally fall inward and slam into the moon at tremendous speed. Each impact vaporizes the comet's water content, scatters it across the lunar surface, and some fraction of those molecules eventually migrate into cold traps. Carbonaceous meteorites carry water locked inside hydrated minerals, not liquid, but chemically bound, which gets released on impact. And then there is the solar wind, a constant stream of protons, which are hydrogen ions, flowing outward from the sun at around 1 million miles per hour. When those hydrogen ions strike oxygen-rich minerals in lunar soil, they can chemically react to form hydroxyl groups, OH, which can combine to produce water molecules, H2O, directly in the regolith. No comets required. The moon may be quietly manufacturing small amounts of water from the raw ingredients the sun itself provides. Every single day? Now stop here. If this water has been sitting in those craters for 3 to 4 billion years, if it arrived via comets and meteorites and solar wind chemistry from the earliest epochs of the solar system, something had to deliver it. Something had to carry it across the void of space and deposit it precisely where the moon's geometry would preserve it forever. What do you think put it there? The answer to that question reaches back to the formation of the solar system itself, to the same violent, chaotic bombardment of space debris that also seeded the early Earth, with the water now filling its oceans. The moon's ice may be a direct, frozen record of the same cosmic event that made life on Earth possible. The same ancient delivery system, locked in the dark, untouched. What makes this ice truly extraordinary, beyond its sheer existence, is its condition. It has not been disturbed. No tectonic activity has mixed it into deeper rock. No rainfall has dissolved it. No biological process has consumed or transformed it. The ice in the PSRs is pristine. Some of it is almost certainly older than Earth's oceans. Some of it may predate the first living cell on this planet. The estimated scale of this reservoir is staggering. Based on data from multiple orbital missions, scientists estimate there may be anywhere from hundreds of millions to billions of metric tons of water ice distributed across the lunar poles, concentrated in the PSRs, but also mixed into the regolith at varying depths. Lake Tahoe, sitting on the border of California and Nevada, holds about 37 cubic miles of water. The total water ice on the moon could be enough to fill dozens of Lake Tahoes, sitting in permanent darkness, waiting. The universe, it turns out, is a spectacular refrigerator. It has kept water at negative 248 degrees Celsius for billions of years perfectly preserved, not a molecule out of place. Meanwhile, your refrigerator at home cannot keep a carton of milk fresh past 2 weeks without you checking the seal. For decades, though, none of this was believed. The idea that the moon held water ice, that this dead, airless rock had quietly been accumulating one of the most precious substances in the universe, was dismissed, doubted, and nearly buried by the very scientific community that should have been racing to confirm it. But for decades, nobody believed this was real, and the story of how science almost missed one of the greatest discoveries in human history is even stranger than the ice itself. In 1976, the Soviet Union did something no one had done before, and no one would do again for nearly half a century. They landed a spacecraft on the moon, drilled into its surface, and brought the soil back to Earth. The mission was called Luna 24. It returned with 170 grams of lunar regolith, small enough to fit in your palm, but scientifically priceless. Soviet scientists analyzed the samples, and buried in that data was something that should have shaken the entire field of planetary science to its core. The soil contained water bound within the mineral structure of the regolith at a concentration of 0.1% by weight. That may sound trivial, but 0.1% across a moon-sized body of rock is not trivial at all. The Soviet team published their findings. They sent the results to the wider scientific community. They said, plainly, there is water on the moon. The Western scientific establishment looked at the data, and then, methodically, they dismissed it. The explanation offered was reasonable on its surface. The samples, critics argued, had been contaminated during the return journey. Earth's atmosphere is full of water vapor. The moment those sample containers were opened, or even before, if the seals weren't perfect, terrestrial moisture could have infiltrated the material. The water signal wasn't lunar. It was Earth. It was a measurement artifact. It was human error dressed up as discovery. And with that, the door closed. Not gently. It slammed shut. For nearly 2 decades, the possibility that the moon harbored water was treated less as an open scientific question and more as a settled matter. The consensus hardened the moon is dry. The Soviet result was contamination. Move on. Think about what that decision cost. Nearly 20 years of research momentum abandoned. An entire generation of planetary scientists who never seriously pursued lunar water because the field had already made up its mind. And here's what makes it worse. The Soviet scientists weren't wrong. They were right. They just couldn't prove it in a way the scientific community would accept. And so the truth sat on a shelf and gathered dust while the consensus marched in the opposite direction. Then came 1994. NASA launched Clementine, a joint mission with the Department of Defense, originally designed to test sensor technologies in the harsh environment of space. It wasn't primarily a water hunting mission, but as it orbited the moon and swept its instruments across the South Pole, something unexpected appeared in the radar data. A signal, an anomaly, a reflection pattern at the bottom of permanently shadowed craters that didn't quite match what you'd expect from bare rock. The team published their analysis in 1996. Their conclusion was careful, but clear. The radar signature was consistent with the presence of water ice at the lunar South Pole. The science community's reaction was immediate and almost entirely skeptical. The criticism came from multiple directions at once. Radar signals, detractors pointed out, can be produced by smooth, solid rock surfaces just as easily as by ice. The geometry of the reflection, they argued, could be explained without invoking water at all. The Clementine data was ambiguous. It was suggestive, not conclusive. And in science, suggestive without conclusive is just another word for unproven. So again, the finding was shelved, not disproven, just doubted into irrelevance. Lunar Prospector arrived in 1998, and this time the evidence got harder to explain away. The spacecraft carried a neutron spectrometer, an instrument designed to detect hydrogen by measuring how incoming cosmic rays interacted with the lunar surface. Hydrogen is the key element in water, and Lunar Prospector found it concentrated, distinctly elevated, right at the north and south poles, not scattered randomly. Concentrated, exactly where cold traps would be expected to accumulate water ice over billions of years. The data was strong, stronger than anything before it, but it was still indirect. Detecting hydrogen doesn't prove water. Hydrogen can exist in other forms. The spectrometer couldn't tell you whether what it was seeing was H2O, or hydroxyl, or hydrogen embedded in some other mineral compound. It was circumstantial evidence, compelling, but not airtight. The lesson embedded in this 30-year stretch of near misses is one of the most uncomfortable truths about how science actually works. In theory, science follows the evidence wherever it leads. In practice, science is practiced by human beings, and human beings have priors, frameworks, and deeply ingrained assumptions about how the world is supposed to work. When evidence challenges those assumptions, the first instinct is rarely, let's revise what we believe. The first instinct is, let's figure out what's wrong with the evidence. The moon had been declared dry. That verdict shaped everything. Which instruments got funded, which missions got approved, which research questions were considered worth asking. When Luna 24 returned a water signal, the framework said contamination. When Clementine returned a radar anomaly, the framework said smooth rock. When Lunar Prospector returned elevated hydrogen, the framework said not conclusive enough. 3 separate pieces of evidence from 3 separate missions, spanning more than 2 decades, and each time, the same verdict: insufficient. It's like finding a wet patch on your kitchen floor, smelling something distinctly like water, and noticing the ceiling above it is damp. But because your landlord assured you the roof was perfectly sealed, you spend 30 years telling yourself you probably just imagined it. Does science ever let its assumptions get in the way of the truth? The answer, uncomfortable as it is, appears to be sometimes yes. And the story of water on the moon is one of the clearest examples in modern planetary science of a community that was so certain it knew the answer that it kept finding ways to disqualify the question. 30 years, 3 missions, 3 findings that pointed, each in their own way, toward the same conclusion, and 3 times the field pulled back from the edge of confirmation. In fairness, the skeptics weren't being irrational. The contamination argument for Luna 24 was legitimate. The radar ambiguity for Clementine was real. The indirectness of Lunar Prospector's hydrogen signal was a genuine limitation. None of those individual objections were unreasonable. But 30 years of reasonable objections, stacked on top of each other, starts to look less like scientific rigor and more like institutional stubbornness. 30 years of refusing to believe the moon had water, which, in retrospect, makes science look considerably more hard-headed than anyone might be comfortable admitting in a peer-reviewed journal. The problem, ultimately, wasn't the scientists. It was the tools. Every piece of evidence gathered up to that point was indirect. Radar reflections, neutron counts, chemical trace analysis of samples that may or may not have been sealed properly during a return journey from the moon. What the field needed, what it had never had, was a direct measurement, a device sensitive enough to look at the lunar surface and say, unambiguously, that is water. That molecule, right there, confirmed. That instrument didn't exist on any spacecraft that had visited the moon before 2008. And without it, the debate was always going to stay exactly where it was stuck between suggestive and conclusive, between possible and proven, between a finding and a fact. The moon had been keeping it secret, not because it was hiding anything, but because no one had yet arrived with the right key. And then, someone decided to skip the instruments entirely and just crash a spacecraft directly into the moon to see what came flying out. In 1999, Lunar Prospector had been orbiting the moon for about 18 months. Its neutron spectrometer had done its job. The hydrogen data was collected, published, and sitting in the middle of an unresolved scientific argument. The mission was ending. The spacecraft was running low on fuel, its operational life nearly complete. Someone had an idea. Instead of simply letting Lunar Prospector drift into a random decay orbit and impact to the surface somewhere unremarkable, why not aim it? The South Pole, the permanently shadowed craters. If there really was ice down there, a high-speed impact might vaporize some of it, blasting a plume of water vapor and debris high enough above the crater rim to be detected by telescopes on Earth and in orbit. It would be, in a sense, the moon's own ice testifying on its behalf. One final experiment from a dying spacecraft, a last shot at the truth. The plan was approved. On July 31st, 1999, Lunar Prospector impacted the lunar surface near the South Pole at a speed of 6,100 kilometers per hour. The kinetic energy released was equivalent to 385 pounds of TNT. Telescopes around the world, including the Hubble Space Telescope, were trained on the impact site, waiting for the plume, waiting for water. Nothing appeared. No detectable water vapor, no ice signature in the ejecta cloud. The impact produced a dust plume too faint to analyze clearly, and within the instrument sensitivity available at the time, there was simply nothing there to confirm. The scientific community's disappointment was audible. For many researchers, this was the moment the water hypothesis quietly died. The moon had been hit hard in exactly the region where water was supposed to be, and it had given nothing back. Several teams went further. They published assessments concluding that the null result significantly weakened the case for polar ice. If the ice was there and the impact was in the right place, they argued, something should have shown up. The absence of a signal was itself a signal. The no water camp felt vindicated. But the post-mortem analysis, conducted over the following years, revealed a more complicated picture. The impact point, it turned out, may not have been inside the deepest part of a permanently shadowed region, meaning it may have struck regolith with little to no ice concentration. The angle of impact was not optimized to maximize ejecta height. And critically, the telescopes and spectrometers monitoring the event were operating at the edge of their detection limits. If only a small amount of water ice was present, say, mixed into the soil at low concentration, rather than sitting as a pure surface deposit, the instruments of 1999 simply weren't sensitive enough to see it. This is the brutal reality of exploring something you can't visit. Finding water on the moon is not like finding a lake from an airplane obvious, unmistakable, visible from miles away. It's more like trying to detect a single drop of water mixed into a ton of dry sand. From 238,000 miles away, with instruments that have never been calibrated for exactly this task. Even if you're looking in roughly the right place, you need the right tool, the right geometry, the right angle, and the right moment of impact. Get any one of those wrong, and the ice can be sitting right beneath the impact point and you'll see nothing. What the field was missing wasn't courage or commitment. There was plenty of that. What it was missing was a specific class of instrument, an infrared spectrometer, sensitive enough to detect the precise spectral fingerprint of water molecules in real time at the lunar surface. Infrared spectroscopy works by measuring how materials absorb light at different wavelengths. Water has a distinct absorption signature, a set of wavelengths it consumes in a way that no other common substance does. If you point a sufficiently sensitive infrared spectrometer at a surface containing water molecules, those molecules announce themselves, unambiguously, no inference required. No such instrument had ever been placed in lunar orbit before 2008. Every mission before that date was working with tools designed for other purposes, adapted to a question they weren't built to answer. It was like trying to diagnose cancer by looking at a patient's face. A skilled doctor can notice things, pallor, weight loss, visible symptoms, but no matter how good the doctor is, they cannot see a tumor with their eyes. For that, you need an MRI. The technology has to match the question. Lunar Prospector's crash was not a failure of science. It was a failure of instrumentation, meeting an impossible standard. The scientists who aimed that spacecraft at the South Pole were doing the most they could with what they had. They were creative, they were bold, and they were right to try. But the universe doesn't reward boldness without precision. The ice, if it was there, wasn't going to reveal itself to an instrument that couldn't speak its language. If you had been a planetary scientist in the year 2000, sitting with the Lunar Prospector null result on your desk and the Clementine controversy still unresolved and the Luna 24 contamination argument still echoing through the literature, would you have kept going? Or would you have looked at 30 years of ambiguous results and concluded that the answer was simply no? Most researchers, quietly, chose the second option. The funding dried up, the missions pivoted. The question of lunar water receded from the front lines of planetary science and settled into the background, an open question. Technically, but not one anyone expected to resolve soon. Throwing a spacecraft worth hundreds of millions of dollars into the moon and detecting nothing is, objectively, the most expensive way possible to confirm that you need a better plan. But that's exactly what Lunar Prospector did, and in the strange, nonlinear logic of scientific progress, that expensive null result was precisely what sharpened the thinking for what came next. Because the answer, when it finally came, arrived from a direction no one in the American scientific establishment had anticipated. Not from NASA, not from ESA, not from any of the agencies that had spent decades circling this question. The real answer came from somewhere nobody expected, not from NASA, but from a country sending its very first spacecraft to the moon. Chandrayaan-1 was India's first mission to the moon. Launched on October 22, 2008, by the Indian Space Research Organization, ISRO. It was a landmark moment for a nation that had never before sent a spacecraft into lunar orbit. The mission carried 11 scientific instruments from space agencies across the world. Most of them were built to study the moon's mineralogy, its surface composition, its topography. One of them was built by NASA. And that one, almost by accident, was about to end a 30-year argument. The instrument was called the Moon Mineralogy Mapper, known as M-Cubed. It was an imaging spectrometer, exactly the class of tool that the previous section of this story identified as the missing piece in every lunar water search before 2008. M-Cubed operated in the near-infrared range of the electromagnetic spectrum, measuring how the lunar surface absorbed and reflected light across 85 different wavelength channels simultaneously. Water molecules have a specific, unmistakable absorption signature in the infrared. When light at certain wavelengths, particularly around 2.8 to 3.0 micrometers, strikes a surface containing H2O or hydroxyl, those molecules absorb it in a pattern that nothing else replicates. It is, in effect, water's fingerprint, and M³ was sensitive enough to read it. On September 24, 2009, nearly a year after Chandrayaan-1 reached lunar orbit, a team of scientists led by Carl Peters of Brown University published their findings in the journal Science. The title was precise, the language was careful, and the conclusion was unambiguous for the first time in history. M³ had directly detected water molecules, H2O and hydroxyl, OH, at the surface of the Moon. Not a radar anomaly, not elevated hydrogen counts requiring interpretation, not a chemical trace that might be contamination, a direct spectral detection, the fingerprint of water, read off the lunar surface from orbit. The scientific community's response was immediate and seismic. 30 years of skepticism, 3 decades of contamination arguments, radar ambiguities, and null results from spacecraft crashes collapsed in a single morning. What Luna 24 had hinted at in 1976, what Clementine had suggested in 1996, what Lunar Prospector had implied in 1998, was now confirmed. The Moon had water. The debate was over. But the details of what M³ found were, in some ways, more surprising than the finding itself. The water signal didn't appear only at the poles. It showed up across the entire lunar surface at equatorial latitudes, at mid-latitudes, in sunlit regions where, by every prior expectation, water molecules should have been boiled off within hours of arriving. The concentration was extraordinarily low, roughly equivalent to 1 liter of water mixed into 1 metric ton of lunar soil. If you scooped up a cubic meter of moon dirt from the equatorial surface and wrung it out like a wet cloth, you'd extract barely enough water to fill a small drinking glass. It's there, but it's barely there. Yet at the poles, the story changed dramatically. M³ confirmed what the cold trap theory had predicted: water concentration increased significantly toward the lunar poles, consistent with the model of molecules migrating across the surface and becoming permanently frozen in permanently shadowed regions. The polar ice wasn't just a theoretical construct anymore. The infrared data showed it was real, and it was concentrated exactly where physics said it should be. Now consider the technical weight of that word, directly. Every piece of evidence before M³ was indirect. Radar reflections that might be ice, or might be smooth rock. Neutron counts that implied hydrogen, which suggested water, which required several inferential steps before you arrived at a conclusion. Scientists defending those results always had to add qualifiers consistent with, suggestive of, potentially indicating. M³ removed every one of those qualifiers in a single instrument pass. The absorption pattern it recorded at 2.8 to 3.0 micrometers is the spectral fingerprint of water, not approximately, not arguably. Exactly. That is what water looks like in infrared, and that is what M³ saw thousands of times across thousands of square kilometers of lunar surface. This distinction matters enormously. In science, the difference between consistent with water and is water is not a minor semantic point. It is the difference between a hypothesis and a fact. For 30 years, the lunar water question lived in the first category. M³ moved it into the second. And now the backstory. Because this is where the discovery becomes almost implausible in its serendipity. M³ was not Chandrayaan-1's primary mission objective. It was a piggyback instrument, one of 6 foreign payloads included on the spacecraft as part of international scientific cooperation agreements. ISRO's main goals were mapping the lunar surface in high resolution and studying the distribution of minerals. M³ was brought along because it fit within the payload allocation. It complemented the mission profile, and NASA wanted the opportunity to test it in the lunar environment. It was in the hierarchy of mission priorities, a supporting act. The greatest discovery in the history of lunar water science came from a hitchhiker. Think about that for a moment. The question that had consumed planetary scientists for 3 decades, that had launched multiple dedicated missions, that had ended careers, sparked controversies, and consumed hundreds of millions of dollars in funding, it was finally answered by an instrument that wasn't even the main point of the trip. It's a little like ordering a pizza. And while the delivery driver is walking up your driveway, he notices a gold vein running through the crack in your sidewalk that you've been standing on your entire life without seeing. If Chandrayaan-1 had never been launched, if ISRO hadn't been ready to fly in 2008, if the international payload agreements hadn't included M³, if the budget or the politics or the engineering timeline had shifted by a year in either direction, how long would it have taken? Another decade. Another generation of scientists building up to the same conclusion through a different instrument on a different spacecraft. The honest answer is that nobody knows. And that uncertainty alone should give you pause about how many other answers are sitting somewhere in the solar system. Right now, waiting for exactly the right instrument to pass overhead at exactly the right moment. India sent its first mission to the moon and solved the problem that NASA, the Soviet Union, and the European Space Agency had spent 30 years circling, which is, depending on how you look at it, either a beautiful testament to the global nature of science, or a rather pointed reminder that being first doesn't always mean being the one who figures it out. That distinction probably explains why NASA, upon digesting the M³ results, decided it was time to stop inferring and start excavating. If detecting water molecules in the soil was the confirmation, then proving the scale of what was actually frozen in those permanently shadowed craters would require something considerably more dramatic than an infrared spectrometer. It would require, in fact, the most deliberately destructive act in the history of lunar science. But detecting water molecules scattered across the surface and confirming billions of tons of ancient ice buried in permanent darkness are 2 entirely different things, and to prove the second, NASA was about to do the most audacious thing it had ever attempted on another world: cross the lunar crater. Observation and Sensing Satellite was designed with a single purpose: not to orbit, not to photograph, not to analyze from a comfortable distance. It was built to crash, deliberately and precisely, into the floor of a permanently shadowed crater at the lunar South Pole, and then measure what came flying out. The architecture of the mission was unlike anything NASA had attempted before. The plan centered on the spent Centaur upper stage rocket that had carried the spacecraft to the moon. A hollow metal cylinder, 2,200 kilograms in mass, essentially a large empty fuel tank traveling at extraordinary speed. This Centaur stage would separate from the L-Cross shepherding spacecraft and impact first, hitting the target crater at 9,000 kilometers per hour. The kinetic energy at the moment of impact would be equivalent to 1.5 metric tons of TNT, nearly 4 times the energy released when Lunar Prospector struck the surface in 1999. Then, 4 minutes later, L-Cross itself would fly directly through the rising debris plume instruments, firing continuously, collecting data at close range before impacting the surface in its own secondary crash. The target was Cabeus Crater, chosen deliberately, based on Lunar Prospector's hydrogen concentration maps and refined analysis from the Lunar Reconnaissance Orbiter, which had arrived in orbit earlier that year. Cabeus sits near the lunar South Pole, its floor locked in permanent shadow, its geometry positioned such that a plume rising from its interior could be observed from above the crater rim by spacecraft in orbit. On October 9th, 2009, at 7:31 in the morning Eastern Daylight Time, the Centaur stage hit the floor of Cabeus crater. The impact was not visible to the naked eye from Earth. The plume rose, but faintly, far below the threshold of unaided human vision. Telescopes and spectrometers watching from orbit and from Earth's surface tracked the ejecta cloud as it rose above the crater rim. 4 minutes passed. L-Cross flew through the plume. Every instrument it carried recorded the encounter. Then it too struck the surface, and the mission was complete. The science team processed the spectral data. What they found was not ambiguous, not suggestive, not open to alternative interpretation. The infrared and ultraviolet spectrometers aboard L-Cross detected H2O water clearly and unmistakably in the debris cloud. They also identified carbon monoxide, CO, hydrogen sulfide, H2S, ammonia, NH3, and traces of additional organic compounds that planetary scientists had not fully anticipated finding. Cabeus crater was not simply a reservoir of frozen water. It was a chemical archive, a frozen inventory of billions of years of volatile compounds delivered by comets and meteorites, preserved in the dark at temperatures that prevented any chemical alteration. The official published figure, at least 155 kilograms of water vapor and ice, were present in the debris cloud from the Centaur impact alone. 155 kilograms from a single strike zone, roughly the size of a large house. Extrapolating that concentration across the full extent of Cabeus and the network of permanently shadowed regions mapped across the lunar South Pole, scientists calculated the total water ice reservoir at hundreds of millions of metric tons. Later analyses extended that estimate further. Between 2018 and 2020, combined data from L-Cross, the Lunar Reconnaissance Orbiter, and the Moon Mineralogy Mapper on Chandrayaan-1 produced refined models pushing some estimates toward the lower range of billions of metric tons distributed across the permanently shadowed regions of both lunar poles. The numbers shifted as methodologies improved, but the direction never changed. Every new analysis found more, not less. To translate that into something graspable, an Olympic swimming pool holds 2,500 metric tons of water. Hundreds of millions of metric tons of lunar ice, even at the conservative end of the estimates, represents the equivalent of tens of thousands of Olympic swimming pools. All frozen, all buried, all sitting in darkness that has not been broken since before complex life existed on Earth. Now the question that the confirmation of all this water immediately demands: we know it's there. We know the scale. So what do we actually do with it? NASA crashed 2 spacecraft into the moon across the span of a decade to find this answer. The first time, in 1999. The instruments weren't good enough, and the result was silence. The second time, in 2009. The instruments were right, the target was right, and the result was unambiguous confirmation, which is, honestly, a fairly clean demonstration that in science, persistence always wins, provided you have enough budget left to build another spacecraft. But here is what the raw confirmation doesn't tell you. Knowing the water is there and knowing what it's worth are two separate problems entirely. The ice in those craters isn't just frozen water. It is 4 billion years of solar system history, locked in chemical form, sitting undisturbed in one of the most extreme environments in the known solar system. And its value properly understood exceeds any natural resource humanity has ever competed over on this planet. But having water and being able to use it are two completely different things. And what that frozen reservoir can actually be converted into is the reason the lunar South Pole has become the most strategically contested piece of real estate in the solar system. The origin of the lunar ice comes from 3 confirmed sources. First, comets' ancient bodies from the outer solar system, composed largely of ice and rock, that periodically fall inward and strike the moon at high velocity. Each impact vaporizes the comet's water content, scatters it across the lunar surface, and some fraction of those molecules eventually migrate into cold traps at the poles. Second, carbonaceous meteorites, a class of space rock containing hydrated minerals, water chemically bound within their crystal structure, released on impact. Third, the solar wind itself. The sun continuously streams outward a flux of protons, hydrogen ions, H+, that bombard the lunar surface at high velocity. When those hydrogen ions strike oxygen-bearing minerals in the lunar regolith, they can chemically bond to produce hydroxyl, OH, and under the right conditions, water molecules, H2O, assembled directly from solar radiation and moon dust. The age of this ice is estimated at 3 to 4 billion years. Some of these water molecules were present before the first single-celled organisms appeared on Earth. Some of them arrived during the late heavy bombardment, the period between approximately 4 billion and 3.8 billion years ago, when the inner solar system was struck by an extraordinary pulse of impactors from the outer solar system. The same comet populations that deposited ice in the lunar cold traps likely contributed to filling Earth's early oceans. The water frozen under the moon's south pole and the water in every ocean on this planet may share the same ancient origin. That's the history. Now the economics, and this is where the story becomes something that extends far beyond planetary science. Why do serious aerospace engineers and strategists refer to lunar water ice as the oil of space? 3 reasons, each one compounding the last. First, drinking water. Right now, delivering 1 kilogram of any payload to the lunar surface costs approximately $1 million, accounting for launch, transit, landing, and mission overhead. Water is heavy. 1 liter weighs 1 kilogram. A crew of 4 stationed on the moon for 6 months would require a minimum of several thousand liters of drinking water, before accounting for hygiene and food preparation. Shipping that from Earth would cost billions of dollars for water alone. If water can be extracted from lunar ice, processed, and purified on site, that cost drops to the price of running the extraction equipment. The logistics transform from a crippling constraint into a manageable engineering problem. Second, oxygen. Water is H2O2 hydrogen atoms and 1 oxygen atom per molecule. Split water with electrical current through a process called electrolysis, and those atoms separate into hydrogen gas and oxygen gas. Oxygen is breathable air. A pressurized lunar habitat requires a continuous oxygen supply. Currently, that supply must either be carried from Earth at enormous cost or recycled within a closed-loop life support system that still requires periodic replenishment. Locally produced oxygen from lunar ice electrolysis closes that loop far more effectively. No supply chain across 238,000 miles. No mission-critical dependency on a launch schedule. The moon itself provides the air. Third, and most consequential for the long-term future of space exploration, rocket fuel. The hydrogen released by electrolysis, when liquefied and combined with liquid oxygen, forms the most efficient chemical propellant in practical use today. Liquid hydrogen and liquid oxygen. The propellant combination used in the Space Shuttle's main engines, in the upper stage of the Saturn V, and in the core stage of NASA's Space Launch System, achieves a specific impulse of approximately 450 seconds. Specific impulse is the measure of propellant efficiency. Higher is better, and 450 seconds sits near the ceiling of what chemical propulsion can achieve. A rocket launched from the moon requires a fraction of the propellant needed to launch the same payload from Earth. The moon's surface gravity is 1/6 of Earth's. Its escape velocity is 2.38 kilometers per second against Earth's 11.2 kilometers per second. The physics of this difference, compounded across a mission to Mars or beyond, is enormous. A spacecraft departing Earth for deep space must first climb out of a deep gravitational well through a dense atmosphere, carrying all the fuel it needs from the moment of liftoff. A spacecraft departing the Moon starts from a shallow gravitational well with locally produced propellant already loaded. This is why the analogy to a gas station holds and why it actually understates the case. Imagine you need to drive from New York to Los Angeles, but the only way to carry fuel is to load every drop you'll need at the starting point. The weight of the fuel itself limits how fast you can go and how much cargo you can carry. Now imagine there is a refueling station in Kansas, stocked with locally produced fuel, where you can stop, refuel, and continue with a much lighter vehicle. The range of your journey increases. The cost per mile drops. Destinations that were marginal become reachable. That is what a lunar fuel depot built on extracted water ice represents for missions to Mars and the outer solar system. The Moon, positioned at the edge of Earth's gravitational sphere of influence, functions as a natural waypoint, not a destination, a staging ground. Whoever builds the infrastructure to extract water ice, electrolyze it into propellant components, liquefy and store those components, and transfer them to departing spacecraft, that entity holds a logistical position in space operations that compounds with every mission launched. It is leverage, and in space, where propellant mass ratios govern everything, leverage is power. Do you think humanity is standing at the threshold of a genuine space energy revolution? Because the engineers who have run these numbers believe the answer is straightforwardly yes. The question is only who builds the infrastructure first, and under what terms the rest of the world gains access to it. The lunar ice has been sitting in those craters for 3 to 4 billion years, completely indifferent to human ambition and political competition, waiting to be collected. It is, in the most literal sense, a first-class ticket to the rest of the solar system, and it has been sitting unclaimed in the dark for longer than complex life has existed on this planet. But before any nation can collect that ticket, before a single kilogram of lunar ice can be melted, split, or loaded into a propellant tank, there is an environment waiting at the bottom of those craters that has already broken every machine sent to face it. To extract the ice, you have to go in. There is no remote option, no way to reach the permanently shadowed regions from a comfortable distance with a long arm or a clever antenna. The ice is on the floor of those craters. The equipment has to go down there into total darkness, into negative 248 degrees Celsius, into a place where there is no sunlight whatsoever to generate electrical power. That is the engineering reality, and it is brutal in ways that don't fully register until you start listing what happens to machines at that temperature. At negative 248 degrees Celsius, most metals undergo a phenomenon called cold embrittlement. Steel, aluminum alloys, and many other structural materials that are strong and flexible at room temperature become brittle, liable to crack or shatter under mechanical stress rather than bend. A rover wheel striking a sharp rock at those temperatures doesn't dent. It fractures. Lubricating oils the fluids that allow gears, bearings, axles, and hinges to move against each other without seizing freeze solid long before you approach those temperatures. Standard lubricants fail somewhere between negative 40 and negative 80 degrees Celsius. At negative 248, there is no lubricant on the commercial market that remains functional. Wheels lock, joints seize, drill mechanisms jam after the first rotation. The rover you spent $2 billion designing, testing, and launching stops moving within minutes of entering the shadow. The electrical systems face a separate catastrophe. Lithium-ion batteries, the dominant energy storage technology in modern spacecraft. Rovers and landers lose approximately 80% of their effective capacity at extreme cold. The chemistry of the battery requires ion movement between electrodes, and at cryogenic temperatures, that movement slows to near zero. A battery rated for 100 watt-hours at room temperature delivers roughly 20 watt-hours in a PSR. That's not a performance degradation. That's a mission-ending failure. The evidence for all of this is not theoretical. It is written across the recent history of lunar exploration in a series of missions that each, in their own way, hit the same wall. Chandrayaan-2's Vikram lander launched in July 2019. India's second lunar mission and its first attempt at a soft landing. The target was the lunar South Pole region, the first time any nation had attempted to land that close to the pole. Vikram descended through the final phase of its approach on September 7th, 2019. At an altitude of 2.1 kilometers above the surface, contact was lost. The lander struck the surface at high velocity. Post-mission analysis attributed the failure to a software anomaly in the braking thrusters during final descent. India had come within 2 miles of becoming the 4th nation to land on the moon and the first to reach the South Pole before the mission ended in 2.1 kilometers of silence. 4 years later, Chandrayaan-3 succeeded where its predecessor had not. On August 23, 2023, Vikram's successor touched down near the lunar South Pole, making India the first country in history to land a spacecraft at the lunar South Polar region, and only the 4th nation to achieve a soft landing on the moon at all. The Pragyan rover deployed and began traversing the surface. It operated for approximately 10 Earth days, collecting compositional data, imaging the terrain, transmitting results. Then the lunar night arrived. Temperatures at the surface plunged. Pragyan was designed to hibernate through the night and reawaken when sunlight returned 2 weeks later. It never woke up. The cold had been too much. The mission was declared complete. In January 2024, Japan's smart lander for investigating Moon Slim touched down successfully on the lunar surface, becoming the 5th nation to achieve a soft landing. The landing precision was extraordinary. Slim hit within 100 meters of its target point, a record for lunar landing accuracy. But during the descent, the spacecraft tilted at an angle that left its solar panels pointing away from the sun. It had power for only a few hours. When the battery drained, the mission went dark. Japanese mission controllers waited, and when the sun angle shifted enough weeks later, Slim briefly reactivated, but the window was narrow and the science return severely limited by the initial power failure. 3 missions, 3 different failure modes, 1 common thread power. In a permanently shadowed region, solar panels are useless. There is no light. The only proven power sources capable of operating indefinitely in that environment are radioisotope thermoelectric generators, RTEGs, the same nuclear power systems used by the Curiosity and Perseverance rovers on Mars, and by the Voyager probes still operating in interstellar space. RTGs generate electricity from the heat produced by the natural decay of radioactive material, typically plutonium-238. They work in complete darkness. They work at cryogenic temperatures. They don't require sunlight or a battery charge cycle. But they are expensive. They are politically complex to approve and launch, and they produce relatively modest amounts of power, enough to keep instruments alive, not enough to run heavy drilling or processing equipment. The alternative is running power cables from outside the crater. Establish a solar power station on the crater rim where sunlight is available and transmit electricity down into the PSR via cables or wireless power transfer systems. The distance from rim to floor in a crater like Habeas is several kilometers of steep, rocky, uneven terrain. The cable has to survive the same temperature extremes as the equipment it's powering, and communication is a separate problem entirely. Radio signals cannot pass through crater walls. A rover operating on the PSR floor has no line of sight to Earth or to orbiting relay satellites. It needs either a dedicated relay satellite in a halo orbit above the lunar South Pole, or a series of surface-mounted communication relays positioned along the crater wall. Both add complexity, cost, and additional points of failure. Operating inside a permanently shadowed region is roughly equivalent to attempting a major plumbing repair at 3 in the morning in Fairbanks, Alaska, in January, with no flashlight, while every tool you brought starts freezing solid within 10 minutes of leaving your truck. Except your truck is 238,000 miles away and cannot come to get you. If robots purpose-built, carefully engineered, tested extensively before launch struggle to survive even brief contact with this environment, then how does a human being go in there? The honest answer is very carefully, with extraordinary support infrastructure, and almost certainly not alone. Engineers designing equipment for PSR operations are working on specialized lubricants that remain viscous at cryogenic temperatures, heated mechanical joints, radioisotope-powered heating elements built into rover chassis, and battery systems using alternative chemistries better suited to extreme cold. Each solution adds mass, cost, and complexity. This is the version of ship it and pray that costs approximately $2 billion per attempt, and that's before you factor in the human life support requirements. The solution, it turns out, was never about conquering the darkness. It was about building a bridge between the light and the shadow. The geometry that makes the lunar South Pole so deadly also, by a strange cosmic coincidence, provides the precise conditions needed to survive there. It comes down to one specific feature of the lunar polar landscape, a feature so counterintuitive that it took detailed orbital mapping to fully appreciate, and so strategically important that it has become the single most contested piece of terrain in the entire space exploration program. The concept is called peaks of eternal light. The name is not an exaggeration, because the moon's axial tilt is only 1.54 degrees, nearly perfectly upright. The sun never rises high above the horizon at the lunar poles. It skims along the horizon continuously, circling slowly as the moon rotates. Most surfaces at the poles spend the majority of their time in shadow. But on the highest points, the tallest ridges and peaks along the rims of the major south polar craters, the geometry works in reverse. Those elevated surfaces are almost always in sunlight, catching the low-angle solar rays that continuously sweep around the horizon, while the crater floors below them remain in permanent darkness. The Lunar Reconnaissance Orbiter, which has been mapping the moon in extraordinary detail since 2009, identified and characterized these peaks with meter-level precision. The most significant ones cluster around the rims of the large south polar craters, the rim of Shackleton Crater, portions of the Haworth Rim, and sections of the Noble Rim. These elevated features receive direct sunlight for approximately 89 to 90% of the lunar year. Not all year occasional dips below the solar horizon do occur, but close enough to always that solar panels mounted there can generate continuous, reliable electrical power with only brief interruptions. The strategic implication is immediate and profound. The peaks of eternal light sit just a few kilometers to a few tens of kilometers from the rims of the permanently shadowed regions, the same PSRs that contain the ice. The distance between place where solar power works perfectly and place where the ice is not millions of miles. It is, in some cases, a short rover drive. This proximity is the key that unlocks the entire architecture of a lunar South Pole base. NASA and ESA have both converged on the same fundamental strategy, for the same physical reasons. Build the primary habitat and power infrastructure on a peak of eternal light, where solar panels can run continuously, where temperatures are extreme but manageable compared to the PSR floor, where communications with Earth are relatively straightforward. Then send power and equipment downward into the PSR to extract the ice, process the water at or near the extraction site, or pipe it up to the rim for processing, electrolyze it into hydrogen and oxygen, store the products, use them. The model resembles a mountaintop mining operation. The power plant sits at the peak, the processing facility at a middle elevation, and the extraction equipment descends into the pit below. Except the pit is at -248 degrees Celsius. The processing facility operates in hard vacuum, and the entire operation sits 238,000 miles from the nearest hardware store. NASA has already committed to this strategy in concrete terms. The agency's selection of candidate landing sites for Artemis 3, the mission intended to return humans to the lunar surface for the first time since Apollo 17 in December 1972, includes the region near Shackleton Crater's rim as the top priority zone. Shackleton's rim offers peaks of eternal light within manageable distance of some of the most hydrogen-rich, permanently shadowed regions identified by Lunar Prospector and confirmed by subsequent orbital data. The choice of landing site is not incidental. It is a declaration of strategic intent. The goal is not just to visit the South Pole. It is to establish the infrastructure for sustained operations there. The terrain, however, is not cooperative. The flat Maria Plains, where Apollo landed, carefully selected for their gentle, obstacle-free surfaces, bear no resemblance to the South Polar Rim environment. Crater rims are rough, heavily cratered themselves at small scales, steeply sloped in places, and cut by ridges and scarps that create navigation hazards for both landers and rovers. A spacecraft descending to the Shackleton Rim cannot use the same landing protocols developed for Apollo. The terrain assessment required is far more detailed, the hazard avoidance systems far more sophisticated, and the margins for error considerably smaller. Think of it this way. Building a base at the lunar South Pole is essentially the equivalent of constructing a military installation on a high mountain summit. You have commanding position, abundant energy from the peak, and direct access to the resource below. But resupply is a logistical nightmare. The terrain makes every movement complicated, and one infrastructure failure cascades quickly into a life-threatening situation. Multiply those challenges by the vacuum of space, the radiation environment, the communication delays, and the distance from any possible rescue, and you have an engineering problem of a scale that makes the construction of the International Space Station look straightforward. What's the single biggest challenge of building a lunar base? The terrain, the power systems, the cold, the communications, the dust. Every engineer working on this problem will give you a different answer, and every one of them is right. There is no single biggest challenge. There is a cascade of them, each one requiring a solution that creates the conditions for the next problem to become solvable. It is engineering as a chain reaction, where each link has to hold before the next can be tested. Humanity is, in essence, preparing to build a home on the rim of a volcanic crater, in space, specifically so it can dig into the wall next door and extract water. This is objectively the most ambitious and most expensive real estate development project in the history of the species. And the location was not chosen for its views or its livability. It was chosen because the ice is there. But even if you solve the power, the cold, and the terrain, the moon has one more weapon that nobody anticipated until the Apollo crews brought it home on the soles of their boots. The Apollo astronauts reported something strange. On multiple missions, several crew members orbiting the moon in the command module just before lunar dawn, before the sun crept above the horizon on the surface below, saw a faint, diffuse glow along the lunar horizon. Soft streamers of light rising above the surface where nothing should have been glowing at all. No atmosphere, no weather, no clouds, just light, hanging where physics said there should only be darkness and rock. It took decades to fully understand what they were seeing. The answer, when it came, reframed one of the most persistent engineering challenges facing every future lunar mission. What those astronauts observed was not an optical artifact, not instrument error, not the kind of phenomenon you could dismiss once you understood the mechanism. It was lunar dust, floating, not blown by wind, there is no wind, not thrown up by impact. No meteorite was striking at that exact moment on every orbit. Floating because it was electrically charged, repelled from the surface by the same charge carried by the grains around it, drifting upward into the vacuum in a slow, continuous, invisible fountain of microscopic particles. The mechanism behind this begins with the sun and with the solar wind. Ultraviolet radiation from the sun strikes the lunar surface and ejects electrons from the topmost layer of regolith grains through a process called the photoelectric effect. Those ejected electrons leave the surface grains with a net positive charge. Meanwhile, the solar wind, that constant stream of electrons and protons flowing outward from the sun at roughly 1 million miles per hour, bombards the surface from the other direction, depositing charge on a continuous basis. The interaction between these two charging processes is not uniform. On the sunlit side of the moon, UV photoionization dominates, leaving the surface positively charged. On the dark side, electron bombardment from the solar wind dominates, leaving the surface negatively charged. The boundary between those two regions, the terminator line between lunar day and night, is where the electrical differential becomes extreme. Positively charged dust grains on the sunlit side near the terminator experience a strong electrostatic repulsion from equally charged neighbors. Repelled upward with no atmosphere to impede them, fine particles levitate off the surface. The electric field gradient across the terminator then drives those suspended, charged particles in a specific direction from the positive sunlit zone toward the negatively charged dark zone. The dust doesn't drift randomly. It drifts with purpose, following the electrical gradient, migrating continuously from light into shadow. This is not a theoretical model. The Lunar Atmosphere and Dust Environment Explorer LADEE spent approximately 6 months in low lunar orbit between September 2013 and April 2014, specifically designed to study this phenomenon. LADEE's instruments confirmed the existence of a persistent, stable layer of levitating dust extending from near the surface to altitudes of several kilometers above it. Not a momentary disturbance, a continuous, stable feature of the lunar environment, maintained by the ongoing interaction between solar radiation and the surface. Dust floating in vacuum, with no wind to move it, and no gravity strong enough to immediately return it, sustained indefinitely by electrostatic forces. The consequences for a permanently shadowed region are direct and serious. Charged dust migrating from the sunlit terminator region flows continuously toward and into the PSRs, the dark zones that carry the opposite charge and act as the electrical sink for the entire system. Over time, this means the surface of the ice deposits inside permanently shadowed craters is being continuously coated by incoming electrostatically driven dust. A layer of fine, charged regolith settles over the ice, building up slowly but persistently, insulating the surface below. For equipment operating inside a PSR, the implications extend further. Any surface, a solar panel, a sensor window, a mechanical joint cover, a camera lens, a thermal radiator will accumulate charged dust through electrostatic attraction. The dust doesn't need to fall from above or be kicked up by rover wheels. It migrates to charged surfaces on its own, drawn by the same electrical forces that drive it across the terminator. A piece of equipment lowered into a PSR will begin acquiring a dust coating within hours of arrival, regardless of how carefully it was handled. This is where the analogy becomes almost comically accurate. If the stakes weren't so high, imagine vacuuming your house thoroughly, every surface clean, and then watching as the dust outside your windows begins rolling in through every gap in the door frame, every crack in the weather stripping, every millimeter of space where the seal isn't perfect. You cannot clean faster than it accumulates. You cannot seal the building completely without also sealing yourself in. And the dust carries a static charge that makes it cling to every surface it touches with a grip that a cloth cannot remove. That is the situation facing every piece of equipment and every habitat placed on the lunar surface. The dust does not wait to be disturbed. It arrives on its own schedule, following the electric field, and it does not leave. A lunar base cannot simply avoid the dust problem. By choosing a clean location or by keeping equipment sealed, the dust finds its way to every charged surface. Thermal control systems. The radiators that regulate equipment temperature in the absence of atmosphere accumulate dust layers that reduce their emissivity and cause electronics to overheat. Optical instruments lose clarity as particle films build on lens surfaces. Mechanical joints and seals acquire grit in their interfaces. Power transmission efficiency drops as dust coats solar panel surfaces that weren't inside the PSR to begin with. The problem is not localized. It is systemic and continuous, which raises a question worth sitting with honestly. Between the cold and the dust, between an environment that freezes machinery solid and one that silently coats every surface with electrostatically bonded abrasive particles, which one poses the greater long-term threat to sustained human operations on the moon? Engineers working on this problem will tell you the cold is more immediately dangerous, but more tractable. You can design around it with the right materials and power systems. The dust is slower, but harder to fully solve, because it exploits every surface, every gap, every moment the equipment is exposed. It is relentless in a way that cold is not. Cold stays where you expect it. Dust follows you. The greatest technical challenge of the 21st century lunar program is not the rocket equation, not nuclear power generation, not life support chemistry. It is dust. Specifically, dust that carries an electrostatic charge and actively wants to attach itself to everything it encounters. This is objectively the most expensive and most technically sophisticated housekeeping problem in human history. A $2 billion vacuum cleaner problem, except the dust replenishes itself from the electric field of the sun, and no vacuum cleaner currently designed can operate continuously at negative 248 degrees Celsius. But the dust doesn't stop at destroying equipment. What it does to the human body, in ways that nobody in the Apollo program fully understood until decades after the last mission returned, is far more disturbing than anything the machines have had to endure. The fundamental difference between lunar dust and any dust you have ever encountered on Earth comes down to a single process, or rather, its complete absence. Every particle of dust on Earth has been shaped by erosion. Wind grinds grains against each other over centuries. Water tumbles them down riverbeds, rounding their edges, smoothing their surfaces. Repeated impact, friction, and chemical weathering transform sharp fragments into rounded, relatively harmless specks. Pick up a handful of beach sand and look at it closely. Each grain is smooth, its edges worn away by millions of collisions over thousands of years. That erosion is what makes terrestrial dust fundamentally inert. It has been beaten into submission by the physical world around it. Lunar dust has never experienced any of that, not once. In 4 billion years of sitting on the surface of the moon, in a world with no wind, no water, no rainfall, no chemical weathering, and no biological activity of any kind, the particles have remained exactly as they formed as shattered fragments of rock and glass, produced by meteorite impacts and micrometeorite bombardment, each one retaining the jagged, angular, razor-edge geometry of freshly broken material. Under a scanning electron microscope, lunar regolith particles look like shards of broken glass mixed with barbed hooks. The edges are not rounded. They are acute. They are, in the most precise mechanical sense, sharp. The size distribution compounds the danger. The majority of lunar dust particles fall below 20 micrometers in diameter, smaller than a human red blood cell, which measures approximately 7 to 8 micrometers. Many particles are far smaller than that. In the submicron and nanometer range, they are invisible to the naked eye. They settle on surfaces silently. They enter enclosed spaces through gaps too small to see. And because they carry an electrostatic charge, as the previous section established, they do not merely fall onto surfaces, they are drawn to them, anchored by electrical attraction on top of the mechanical grip provided by their jagged geometry. You cannot brush them off. A cloth dragged across a dust-coated surface doesn't remove the particles it gets embedded with them. The Apollo program documented this in real time, across multiple missions, in ways that alarmed engineers even then. Dust accumulated on the visors of astronaut helmets within hours of surface activity, not days. Hours scratching and hazing the optical surfaces to the point where visibility was measurably degraded. After each extravehicular activity, the suits came back into the lunar module coated in fine gray regolith. The dust penetrated the joints and seams of the pressure suits, the articulated sections at shoulders, elbows, wrists, and knees, working into the mechanical interfaces and increasing the force required to move against them. After the Apollo 17 mission, which conducted 3 separate extravehicular activities across 3 days, suit joint degradation was significant enough that engineers flagged it as a concern for any mission of longer duration. The thermal control coatings on equipment were not spared. These coatings, carefully engineered surfaces designed to reflect specific wavelengths of radiation and maintain the temperature of electronics within operational ranges, depend on optical properties that are highly sensitive to contamination. A thin layer of dust changes the reflectivity and emissivity of those surfaces, disrupting the thermal balance. On Apollo missions lasting only a few days, this effect was manageable. Across a 6-month or 12-month stay at a lunar base, the cumulative degradation of thermal control surfaces could push sensitive electronics outside their survivable temperature range. Then there is the case of Harrison Schmitt, a geologist and astronaut on Apollo 17. The final Apollo lunar landing mission. In December 1972, Schmitt spent approximately 22 hours conducting surface operations across 3 separate extravehicular activities. He brought dust back into the cabin on his suit, as all the astronauts did. Within hours of removing his helmet in the pressurized environment of the lunar module, Schmitt began experiencing what he himself described as symptoms resembling hay fever, sneezing, watery eyes, a scratchy throat, nasal congestion, and hoarseness. The symptoms persisted for several hours and then gradually resolved. The crew logged it, NASA noted it, and then the program ended, and the medical implications of that observation sat largely dormant for decades. NASA has since formally identified lunar dust as the foremost technical challenge for long-duration lunar surface missions, a designation confirmed across multiple agency reports published between 2005 and the present. The language in those reports is not hedged. Dust is called a primary hazard to crew health, equipment, longevity, and mission success. It abrades optical surfaces, degrades mechanical systems, compromises thermal control, and enters pressurized environments despite every precaution taken to prevent it. Think of it mechanically this way. Lunar dust acts on every surface. It contacts the way ultrafine sandpaper acts on wood. Except the sandpaper never stops moving, never dulls, never gets replaced. It is continuously abrasive, continuously present, and continuously replenished by the electrostatic drift described in the previous section. You cannot sand the same piece of wood forever without eventually wearing through it. At a lunar base operating for months or years, the cumulative abrasion of dust on suit materials, window seals, airlock mechanisms, and external sensors is not a minor inconvenience. It is a clock counting down toward failure. The solutions currently under active research at NASA read like a list from a science fiction engineering manual. Electrostatic dust shields, surfaces that generate an oscillating electric field to repel charged particles before they can settle. plasma discharge systems that neutralize the charge on incoming dust grains, reducing their adhesion, magnetic field configurations that deflect particles before they reach sensitive surfaces, advanced suit materials with surface chemistries that reduce adhesion at the molecular level. None of these are yet fully proven at operational scale. NASA is, in practical terms, developing the most technically sophisticated and most expensive vacuum cleaning system in human history for the purpose of vacuuming. The ambition of the engineering is almost funny until you remember what happens if the problem isn't solved. Knowing that the dust scratches helmet visors, degrades suit joints, wears through thermal coatings, and triggers allergic responses in astronauts after a single day of surface operations, would you sign up to live on the moon for 6 months? But destroying equipment is one problem. What this dust does inside the human body in ways nobody in the Apollo program recognized until decades after the last mission landed goes far beyond anything the medical community had prepared for. In 2018, researchers at Duke University and Stony Brook University published results from a series of laboratory studies testing the effects of lunar simulant material engineered to replicate the physical and chemical properties of actual lunar regolith on human cell cultures. The studies were not conducted to generate alarming headlines. They were conducted because NASA needed to understand what 6 to 12 months of dust exposure would actually do to a human being, and nobody had ever systematically tested it at the cellular level. The results were not what anyone hoped for. Particles smaller than 20 micrometers, the dominant size fraction in lunar regolith, smaller than a human red blood cell, pass through the upper respiratory tract and penetrate into the deep lung. Standard filtration mechanisms in the nose and throat, which evolved to capture particles of larger size, allow these fine particles through without interception. Once in the deep lung, they trigger an inflammatory response. Chronic exposure produces chronic inflammation, a condition associated with progressive tissue damage, scarring of lung tissue, and reduced respiratory function over time. The mechanism is similar in some respects to silicosis, the occupational lung disease caused by long-term inhalation of fine silica dust in mining and construction work. Lunar regolith is rich in silicate minerals. The parallel is not reassuring. Particles smaller than 100 nanometers. Nanoparticles present in the finest fraction of lunar dust are capable of crossing the alveolar membrane, the thin tissue barrier between the air sacs of the lung and the bloodstream. Once in circulation, these particles do not stay in the lung. They travel. The cardiovascular system carries them to the liver, where they accumulate and trigger oxidative stress, a form of cellular damage caused by reactive molecules that disrupts normal metabolic function. They reach the kidneys. They reach the heart. In each location, the same pattern particle deposition, inflammatory response, oxidative stress, tissue damage accumulating over time. But the finding that stopped researchers cold was not in the lung or the liver. It was in the brain. The blood-brain barrier is one of the most selective protective structures in human biology. A network of tightly joined cells lining the blood vessels of the brain that prevents most substances in the bloodstream from crossing into neural tissue. It is the reason many medications cannot treat brain conditions effectively. The barrier blocks them. Nanoparticles of lunar simulant in the 2018 cell culture studies demonstrated the ability to cross this barrier, not hypothetically. In direct laboratory testing, particles moved from the simulated bloodstream environment into neural tissue cultures. Once in the brain, the particles activated neuroinflammation and immune response in neural tissue that, when acute and brief, serves a protective function, but when chronic and sustained, causes progressive damage to neurons. The inflammatory cascade triggered by foreign particle deposition in brain tissue can impair synaptic function, disrupt the structural integrity of nerve cells, and, over sufficient time, produce measurable cognitive decline. The researchers were testing lunar simulant, not actual lunar soil, but the physical properties that drive these effects, particle size, shape, surface chemistry, are replicated in the simulant with sufficient fidelity that the results cannot be dismissed as artifacts of the experimental material. The cell culture experiment produced a number that is difficult to read calmly. After exposure to lunar simulant, approximately 90% of the lung cell cultures and 90% of the brain cell cultures tested were destroyed. 90%? In a laboratory dish, under controlled conditions. With known concentrations, the material was lethal to cells at rates that no occupational health standard would consider acceptable for any duration of exposure. The DNA findings added another layer. Certain particle types in the fine lunar regolith fraction demonstrated genotoxicity, the ability to cause direct physical damage to DNA strands. Double-strand breaks in DNA, when they occur faster than the cell's repair mechanisms can address them, produce mutations. Accumulated mutations over months of exposure increase the probability of malignant cell transformation. Long-term lunar dust inhalation is not merely an inflammatory hazard. It carries a potential carcinogenic risk that operates on a timeline extending years beyond the end of the mission. Now set that against the exposure context. Apollo astronauts spent 1 to 3 days on the lunar surface. They experienced dust contamination in the cabin. They breathed some fraction of it, and Harrison Schmitt developed acute respiratory symptoms within hours. But 1 to 3 days is not 6 months. It is not 12 months. The cellular damage documented in the 2018 studies is dose-dependent. It scales with duration and concentration of exposure. A brief contact produces a brief insult. Sustained contact produces sustained damage. And no human being has ever been exposed to lunar dust for 6 months. Nobody knows, from direct medical evidence, what that exposure does to the lung, the liver, the brain, or the genome across that timescale. The answer is genuinely unknown. NASA classified this as a showstopper risk their term, used in formal program documentation, for a hazard capable of halting an entire program if not resolved. Not a challenge to be managed, a potential program ender. The agency is currently funding research into suit designs that prevent dust ingress at the collar and wrist seals. Airlock systems that remove dust from suits before the inner door opens. Electrostatic filtration for habitat air circulation. And advanced respiratory protection worn inside the habitat during dust contamination events. Each solution addresses part of the problem. None addresses all of it. Breathing air inside a lunar habitat that has experienced dust infiltration through airlock cycling. Suit ingress. Equipment brought in from outside is not yet a fully solved problem. Inhaling lunar dust is, in the most precise medical terms available, comparable to breathing ultrafine glass fibers that carry an electrostatic charge and are capable of cutting DNA. No standard respirator filters particles in the nanometer range with complete efficiency. No current habitat design guarantees zero dust infiltration across a 6-month mission. The gap between what is known about the hazard and what has been solved about preventing it is real, and it is not small. Should humans live on the moon for extended periods? Knowing this, that question does not have a clean answer yet. The science says the risk is serious. The engineering says solutions are in development. The program says the mission will proceed. Humanity is building a base on the moon while still working out how to prevent brain inflammation. From the floor it's standing on, which is, in the most generous framing possible, the cosmic version of "we'll figure it out as we go." Except the thing being figured out is neurological damage. And yet, knowing all of this, every gram of risk, every unsolved problem, every potentially lethal particle, not one space agency has slowed down. Because what waits at the south pole of the moon is worth more than all the risks stacked together. The race is not coming. It has already started. The Artemis program is NASA's answer to a question that has been sitting unanswered since December 14th, 1972, the last time a human being stood on the surface of the moon. That was Apollo 17. Eugene Cernan climbed back into the lunar module, and as he did, he became the last human to walk on another world. Nobody has gone back since. For more than 50 years, the moon has been visited only by machines. Artemis is not Apollo. The distinction matters, and NASA has been deliberate about making it. Apollo was built around a singular, geopolitical imperative: beat the Soviet Union to the surface, plant the flag, return the crew, declare victory. It achieved exactly that, 6 times over. But the program's scientific and operational architecture was never designed for permanence. Every Apollo mission launched with everything it needed and brought everything back. Nothing was left behind that could sustain a continued human presence. The infrastructure for staying was never built, because staying was never the point. Artemis has a different architecture and a different ambition entirely. The goal is not to visit. It is to establish, not a flag and footprints, but a sustained human presence at the lunar South Pole, the location of the ice, the peaks of eternal light, and the most strategically valuable terrain in the inner solar system. Building a presence there means infrastructure, power systems, habitats, surface mobility, resource extraction capability, communications relay, and the logistical chain to keep all of it running across missions measured not in days, but in weeks and months. Artemis 1 launched in November 2022. The mission carried no crew. Its purpose was to validate the Space Launch System, the SLS rocket, the most powerful launch vehicle NASA has built since the Saturn V and the Orion crew capsule. Orion flew a trajectory that took it around the moon and into a distant retrograde orbit before returning to Earth. The flight lasted 25 days and 600,000 miles of total travel. The capsule splashed down in the Pacific Ocean within the targeted recovery zone. SLS and Orion performed as designed. The foundation for crewed flight was confirmed. Artemis 2 is planned for 2026. 4 crew members, the first humans to travel to lunar distance since Apollo 17, will fly a free return trajectory around the moon without landing. No surface operations, no landing, but a crewed vehicle in cislunar space for the first time in more than 50 years. The psychological weight of that mission will be significant independent of its technical objectives. Artemis 3 is the landing. The target zone is the lunar South Pole region near Shackleton Crater. The same terrain discussed in the context of peaks of eternal light. The same area where Lunar Reconnaissance Orbiter data has identified the highest hydrogen concentrations, the closest proximity between permanent sunlight and permanent shadow. The descent vehicle is SpaceX's Starship, selected by NASA through its Human Landing System program. Starship has never landed on the moon. The mission profile will require orbital refueling of the Starship vehicle in Earth orbit before the translunar injection, burn a complex multi-launch architecture that has no direct precedent in operational spaceflight. The landing will be the first crewed lunar landing in history, targeted at the polar region. The first time any human being has stood in terrain where ice lies beneath the surface within walking distance. Supporting the long-term vision is the Gateway, a small space station planned for a near rectilinear halo orbit around the moon. Gateway is not a destination. It is infrastructure, a waypoint and staging platform for surface missions, providing crew quarters, laboratory space, and docking ports for both crew vehicles and cargo landers. Its orbit is selected to provide communication coverage over the lunar South Pole, addressing one of the relay challenges that makes direct surface-to-Earth communication difficult in polar terrain. Gateway will not be permanently crewed, but it will be available for crews transiting to and from the surface, extending the operational duration of lunar surface missions beyond what a direct Earth-Moon-Earth architecture would allow. The precedent for in situ resource utilization. the technical term for using materials found at a destination. Rather than bringing everything from Earth was already set on Mars. The MOXIE experiment, the Mars Oxygen In Situ Resource Utilization Experiment, flew aboard the Perseverance rover and landed on Mars in February 2021. MOXIE successfully produced oxygen from the Martian atmosphere by electrolyzing carbon dioxide, demonstrating for the first time that a device could generate breathable oxygen from local resources in an actual planetary environment, not a laboratory on Earth. The technology is directly applicable to lunar ice processing. If electrolysis works on Mars with carbon dioxide, it works on the Moon with water. MOXIE proved the concept. Artemis will attempt to prove it at scale. The long-term target is what NASA has described in program documents as a lunar base camp, a semi-permanent installation at the South Pole, capable of supporting crews for stays of several weeks to several months. Not a permanent colony. Not yet, but a functioning, reusable outpost where successive crews can live, work, extract resources, and test the technologies required before the same architecture is extended to Mars. The base camp concept treats the Moon not as a final destination, but as a dress rehearsal. Everything learned about long-duration surface operations, dust mitigation, resource extraction, and closed-loop life support on the Moon reduces the risk and cost of doing the same thing on Mars, 400 times farther away? The cost of all this is not modest. The Artemis program was estimated to cost approximately $93 billion through 2025, based on NASA Inspector General projections. That estimate has continued to rise as schedules have shifted and mission complexity has grown. $93 billion is more than the entire Apollo program cost in inflation-adjusted terms. It is the most expensive space exploration program in history by a significant margin. Apollo cost the equivalent of roughly $180 billion in today's money and planted 6 flags. Artemis is spending $93 billion and climbing to plant the infrastructure for everything that comes after. If the ice at the South Pole delivers on its promise as a propellant source and life support feedstock, the return on that investment compounds with every subsequent mission that doesn't have to carry its consumables from Earth. The economics of it eventually work. Eventually, whether the political will to sustain the program through the decades required to reach that payoff exists is a separate and considerably less certain. Question: do you think humans will actually live on the Moon within this century? Not visit live, maintain a rotating crew, run continuous operations, extract resources on an ongoing basis. The engineers building Artemis believe the answer is yes. The program's budget history suggests the answer depends heavily on what happens in Washington every 4 years. Both things are true simultaneously. But America is not running this race alone, and the competitor on the other side is not following behind. It is running its own schedule, at its own pace, toward the same destination. At least 9 nations and a growing number of private companies currently have specific funded plans for lunar missions between now and 2030. This is not a competition in the abstract sense of nations pursuing parallel scientific interests. It is a race for position for the specific landing zones, the specific crater rims, the specific proximity to ice deposits that will determine who controls the most valuable operational real estate in the inner solar system for the coming decades. China's Chang'e program has been the most consequential competitor to emerge in the past 5 years, and its trajectory is not one of cautious, incremental steps. Chang'e 5 launched in November 2020 and successfully returned 1.7 kilograms of lunar soil samples to Earth. The first sample returned from the Moon since the Soviet Union's Luna 24 mission in 1976, 44 years of gap, closed in a single mission. The samples were from Mons Rimker in the northern Oceanus Procellarum region, and their analysis has produced scientific results that continue to be published in major journals. Chang'e 6 followed in 2024 with something that had never been done before in the history of lunar exploration. The mission landed in the South Pole Aitken Basin, a region on the far side of the Moon near the South Pole, and returned samples from that location to Earth. First sample returned from the lunar South Polar region. First sample returned from the far side of the Moon. First demonstration that China could execute a dual relay communication architecture required because the far side of the Moon has no direct line of sight to Earth, with sufficient reliability to support a surface sample collection and ascent sequence. The mission succeeded completely. The samples are in Chinese laboratories now, being analyzed. Chang'e 7 and Chang'e 8 are planned for 2026 through 2028. Chang'e 7's primary objectives include detailed reconnaissance of South Polar, permanently shadowed regions, direct search for water ice, and characterization of the resource environment. Chang'e 8 is intended to demonstrate in situ resource utilization technology, the same category of capability that MOXIE demonstrated on Mars, but targeted at lunar ice extraction and processing. The Chinese program is not heading toward the South Pole to study it from orbit. It is building toward operating on its surface. The institutional framework for China's long-term lunar ambitions is the International Lunar Research Station, ILRS-A program, developed jointly with Russia, targeting the construction of a robotic base at the lunar South Pole before 2030. The ILRS is designed to operate autonomously without continuous human presence in its initial phases, managed by surface robots and orbital systems, before transitioning to crewed operations in subsequent phases. Several nations have expressed interest in participation. The ILRS represents a parallel international coalition to Artemis, a separate geopolitical bloc organized around the same destination for the same fundamental reasons. India's Chandrayaan-4 mission is in active planning, with South Polar sample return as a primary objective. Japan, the United Arab Emirates, and multiple European Space Agency member states are contributing instruments and systems to the Artemis architecture. SpaceX's Starship is the selected Artemis 3 landing vehicle. Blue Origin's Blue Moon lander has been selected for subsequent Artemis missions. Astrobotic and Intuitive Machines are competing for Commercial Lunar Payload Services contracts, CLPS, delivering scientific and technology demonstration payloads to the lunar surface for NASA on commercial vehicles. The ecosystem around the Moon has expanded from a government-only domain to a mixed public-private competition operating on multiple timelines simultaneously. The legal framework governing all of this activity has not kept pace with the operational reality. The Outer Space Treaty of 1967, the foundational document of international space law, signed by 114 nations, prohibits any country from claiming sovereignty over the Moon or any other celestial body. No nation can own the Moon. That clause is clear. But the treaty was written in an era when resource extraction from other worlds was science fiction, and it contains no specific provision addressing the extraction and use of materials found on those bodies. The question of whether a country can mine lunar ice and use or sell the products without claiming ownership of the territory is legally unresolved at the international level. The United States passed the Commercial Space Launch Competitiveness Act in 2015, asserting that American citizens and companies have the right to own resources they extract from space, even if they cannot own the territory. Several other nations have passed similar domestic legislation. The Artemis Accords, introduced by NASA and the State Department in 2020, establish a voluntary framework for responsible lunar operations, including provisions for safety zones around operating facilities and transparency requirements for lunar activities. By 2024, 43 nations had signed the accords. China and Russia have not. They have separately characterized the Artemis Accords as an American attempt to to establish unilateral rules for a domain that should be governed by broader international consensus through the United Nations framework. The two competing coalitions, Artemis Accord signatories on one side, ILRS partners on the other, are converging on the same location with incompatible legal frameworks and no binding mechanism to resolve disputes over access, exclusion zones, or resource rights if their installations end up in close proximity. The south polar region of the Moon is not infinite. The peaks of eternal light are specific, mappable, limited features. The highest value landing zones, those combining proximity to permanently shadowed regions, relatively smooth terrain, and good solar exposure, are finite in number. If two installations from competing national programs end up within a few kilometers of each other, competing for the same ice deposits and the same solar power, operating under different legal frameworks, with no agreed mechanism for dispute resolution, the situation has no historical precedent in space, but several historical precedents on Earth. None of them ended particularly well. Humanity spent 4 billion years evolving to its current state, 400 years developing modern science, and approximately $1 trillion in cumulative space program budgets across all nations. And the result is a race to claim a patch of frozen shadow on a crater floor, 238,000 miles away. If that sounds like a strange destination for the accumulated ambitions of our species, consider what the ice represents. Consider the propellant, the oxygen, the water, the strategic leverage across the entire solar system. Then consider the fact that the zones most likely to host the largest deposits are small enough that the first nation to establish sustained operations there holds a positional advantage that may be permanent. Who will plant the first permanent base at the lunar South Pole? The honest answer is that nobody knows. Both programs are running behind schedule and over budget. Both face genuine technical challenges that have not been fully solved. Both are dependent on political continuity across administrations and funding cycles that extend well beyond any single election. The race is real, the outcome is open, and the prize is the most consequential piece of ground humanity has ever competed for. But while the nations are planning and negotiating and racing, there is a truth larger than all of it, something that most people, including the scientists building these missions, have not yet stopped to fully recognize. By this point in the story, it feels like the picture is complete. We followed the arc from beginning to end, the permanently shadowed craters, the paradox of ice in a vacuum, 30 years of dismissed evidence, the Soviet discovery that nobody believed, the two spacecraft deliberately crashed into the moon a decade apart, the Indian mission that solved the question as a side project, the confirmed billions of tons of ancient frozen water, the electrical dust that migrates on its own and reaches the brain, the race between superpowers for a patch of frozen shadow on a crater floor, 238,000 miles away. The story has a beginning, a middle, and what appears to be an end. The water is there, the nations are coming, and humanity is finally going to claim what was waiting all along. That is a satisfying conclusion. Clean. Complete. The kind of ending that wraps the evidence into a narrative that feels resolved. It is not the full story. In 2020, a team of researchers using data from SOFIA, the Stratospheric Observatory for Infrared Astronomy, a telescope mounted inside a modified Boeing 747 aircraft flying at altitudes above most of Earth's atmospheric water vapor, published findings in the journal Nature Astronomy that quietly broke the established model without making nearly as much noise as they should have. SOFIA detected molecular water, H2O, not at the lunar poles, not in a permanently shadowed region, not in a cold trap. It detected water molecules in Clavius Crater, a large, ancient impact crater in the lunar southern highlands, at a latitude of approximately 58 degrees south, a sunlit region, a place where, according to every theoretical framework developed over the preceding decades, liquid water cannot exist, and water molecules should be lost to space within hours of arriving. The surface temperature in Clavius during lunar day reaches well above the threshold at which thermal desorption drives water molecules off the regolith and into the exosphere. By every model built on the cold trap hypothesis, water at Clavius should be impossible to sustain. And yet Sophia found it confirmed through the same infrared spectral fingerprint that made the Chandrayaan-1 moon mineralogy mapper results definitive the absorption signature at approximately 6 micrometers, characteristic of molecular H2O, distinguishable from the hydroxyl signal that had confused earlier measurements. Not OH, not something that might be water itself, in the sunlight, at a latitude where it has no theoretical right to persist. The concentration was low, estimated at roughly 100 to 400 parts per million, comparable to the water content of the driest desert soil on Earth. But low concentration is not the same as zero. The molecule is there. The question is why. 2 hypotheses currently compete to explain it, and neither has been fully verified. The first, water molecules at sunlit latitudes are being physically trapped inside tiny glass beads, microbeads, formed by micrometeorite impacts. When a small meteorite strikes the lunar surface, the intense heat of impact melts the surrounding regolith into glass. If water molecules are present at the moment of impact, they can become encapsulated inside these glass structures as they solidify, shielded from the thermal desorption that would otherwise drive them off the surface. The glass prison preserves them against the heat of the lunar day. Under this model, the water Sophia detected is not free on the surface, it is locked inside microscopic glass capsules distributed through the regolith, released only slowly as those capsules are shattered by subsequent micrometeorite strikes. The second hypothesis is more unsettling in its implications. It proposes that the water at sunlit latitudes is not ancient, trapped, or preserved. It is being continuously created. Solar wind protons, hydrogen ions strike the oxygen-bearing minerals of the lunar regolith constantly, every second of every day, on every sunlit surface of the moon. Under the right conditions of temperature, mineral composition, and radiation flux, those protons bond with oxygen to form hydroxyl, and hydroxyl combines to produce water. If this process is ongoing and the rate of production is sufficient to maintain a detectable equilibrium concentration against the rate of thermal loss, then the moon is not merely storing ancient water, it is manufacturing new water, continuously, from sunlight and rock. That mechanism has not been fully verified. The rate calculation required to confirm it demands measurements that current instruments have not yet made with sufficient precision. But the data from Sophia cannot be dismissed, and neither hypothesis offered to explain it has been confirmed to the satisfaction of the full scientific community. The mechanism sustaining water in the sunlit regions of the moon remains, as of now, an open question. Sit with the second hypothesis for a moment, because if it is correct, the implications extend far beyond the moon. If the solar wind reacting with oxygen-bearing minerals produces water continuously on the lunar surface, a body with no atmosphere, no geological activity, no biological chemistry of any kind, then the same process operates on every airless rocky body in the inner solar system bathed in solar radiation. Mercury, the asteroids, the rocky moons of Mars, the surfaces of the outer planet moons where solar wind still reaches, Callisto, Ganymede, both confirmed to have water ice deposits. If solar wind chemistry is producing water on the moon's sunlit surface, it is almost certainly producing water on those bodies as well. Not in the quantities locked in cold traps, perhaps, but present, detectable, potentially harvestable water. Under this model, is not a rare gift delivered by comets to a handful of fortunate worlds. It is something the solar wind actively manufactures wherever hydrogen meets oxygen-bearing rock in sufficient proximity. The universe may be producing water in places we have never thought to look, through a process that requires no comet delivery, no geological activity, no special conditions beyond the existence of a sun and a rocky surface. How many airless bodies in this solar system have oxygen locked in their minerals? Essentially all of them. How many are bathed in solar wind? Every one that orbits close enough to the sun. How many could be quietly producing water through this mechanism right now? Without our knowing, we do not know. We have not looked with the right instruments. We have not asked the question carefully enough, because until Sophia's 2020 result, we did not know the question needed to be asked in quite this way. And this is where the story breaks open into something larger than anything in the preceding 14 parts. We spent 50 years proving that the moon, the object 238,000 miles from Earth, the world we landed on in 1969, the body that has been studied by more telescopes, probes, and orbital missions than any other in the solar system, had water. 50 years, dozens of missions, billions of dollars, 2 deliberate spacecraft crashes, 1 Indian hitchhiker instrument, 1 aircraft-mounted telescope flying through the stratosphere, 50 years to confirm what was under our feet, or rather, above our heads, every clear night. If the moon held a secret that large for that long, a secret that required exactly the right instrument, pointed at exactly the right location, at exactly the right wavelength, operated from exactly the right altitude to avoid atmospheric interference. What does that imply about everything else? Not the outer solar system, not distant galaxies, the moon, the nearest thing to Earth in the universe, the thing your ancestors could see without any instrument at all. That moon was keeping a secret about water for 50 years, and we almost didn't find it because we kept bringing the wrong tools. So the real question, the one that should sit with you long after this ends, is not what is on the moon. That question now has a partial answer, and missions are being built to fill in the rest. The real question is this: what are we missing right now, in plain sight? Because we haven't yet built the instrument that speaks the right language. What is sitting there, obvious in the data we already have, waiting for someone to look at it from a slightly different angle, at a slightly different wavelength, with a slightly different hypothesis? How many Sophia moments are still ahead of us, discoveries not of distant, unreachable things, but of objects we have studied for centuries and still fundamentally misunderstood? The moon is not a destination. It never was. It is a mirror held up close enough that we cannot avoid looking into it, reflecting back a precise and uncomfortable image of how much we think we understand versus how much we actually do. Every time we have looked at it with a better instrument, it has shown us something we did not expect. Every time we have declared the question settled, it has opened a new one. The moon has been there every night of your life. It will be there tonight, and somewhere on its surface, in darkness that has lasted longer than complex life on Earth, and in sunlight that should have burned every drop of water away, something is happening that we do not yet fully understand. The journey to figure out what that journey is just beginning.